Hi, Dr. Sasha here. Welcome to Obsidian Cliff in Yellowstone National Park. So you can't really see it too up here, but just over there, across the highway, is the Obsidian Cliff. Well, you'll see up there. Oh, there we go. Now we're getting some lighting. I thought if I zoomed in, I might be able to get to. Can I actually see some flow banding and probably some different lava flows. So across the street from us, everything's about 600,000, or it's about 100,000 years old. It's the younger of the volcanic eruption. Everything on this side of the trail is about 600,000 years old. And you can see there's quite a beautiful variety of rocks. Now, I'm going to do this sort of like take only pictures, leave only footprints here, because we're in a national park and there's a big sign talking about how people have been stealing rocks from here, so I don't want to be that guy. So one thing I'm noticing about this rock over here, you can see it's kind of reddish. It's the Rhyolite, and you can see it kind of likes to sparkle. Yeah, why does it do that? Those are little crystals of quartz and other inclusions. Rhyolite forms at relatively low temperatures and is, which means there's a lot of stuff that solidified long before while the rhyolite is still liquid, encased in here. And so most rhyolites have at least a vaguely porphyritic texture, some more than others, especially the ones that are particularly rich in pelagic clays, which are rare, but we see a bunch of them in the San Diego area, so yeah. So a couple things you can see, all these little like sparkly crystals here, shimmering in the sun, and yeah, lots of little things here. Now the couple other igneous rocks we have here include this obsidian. This is probably from that cliff. They wanted to give you a little touch tank. And one thing I love about obsidian is that it's the one of the few rocks that is not actually contain any minerals. This rock cooled so quickly that it never formed a regular crystal structure. Now, as you learned during minerals, in order for something to be a mineral, it has to have a regular crystalline structure. In fact, the chemical structure of this is irregular, has no form, and is much more like glass. In fact, they call this stuff volcanic glass. You can see it's got a very glassy texture. It's got this conchoidal fracture, these little concentric circles along the breakage surface.
Do you want me to get up?
And you can see there's even these like air bubble rich layers or bands in between here, because this is a fairly gassy region. Most lava flows here are extra gassy. So, you can see here, I think what we have down here is basalt, just based on its color. It's a little bit hard to tell rocks, but generally darker volcanic rocks, the ones that are sort of more blackish, tend to be basalt, and the lighter grayish reds tend to be rhyolite, and the ones that are truly sort of that intermediate whitish gray are often andesite. This is just sort of like a shoot from the hip thing. You do have to check out the minerals closely under a magnifying lens to truly classify the igneous rock you're looking at, but I thought you might like to do a little, see a little bit how this works in the field and start to look at some of the evidence. Now, of course, in Yellowstone, rhyolite is everywhere. For all the cataclysm, this was actually a very low temperature eruption. Now, certainly full of gas, and there was a lot of stuff going up in the atmosphere at once, and a lot of sulfur, and certainly too hot for my comfort, but by the standards of volcanic eruptions, the ones taking place in Hawaii and Iceland are substantially hotter by several hundred degrees. And so I just want to show one other thing. We see this in a number of places, and I love the way they did this little information kiosk here. In fact, there's two things I love about this information kiosk. One is, you can see all these little columns. They're clearly trying to emulate the hexagonal columnar jointing that happens when lavas cool. Cool, so what happens is, the reason you see all these hexagonal stones here is that as a lava cools, it shrinks, and it solidifies before fully shrinking. Remember, it's still crystallizing at 600 degrees, and the temperature at Celsius, the temperature out here is probably 15 degrees Celsius. It is a freaking beautiful summer day out here. It's which means that's a big temperature difference, and that rock is going to shrink as it gets colder. And so when you have stress from all directions along the cooling surface, the default pattern is cracks that intersect each other at 120 degrees, giving these perfectly hexagonal stones. And the cool thing is, you see this in a wide variety of lavas. You see this in basalts. You see this in andesites. You see this in rhyolites. We have some of these right around San Diego, around Calvary Hill. We call it columnar jointing. Now, to remind you again that there's two mechanisms for classifying igneous rocks. There's composition, which we've been talking a lot about with the color of everything here. There's also texture. This means how long did it have to cool. So our common rhyolite, here's our little touch tank. So remember, obsidian barely had time to crystallize. It just showed up, cooled before anything formed. Your common rhyolite had some time to crystallize in sort of steady state. And then here we have granite. Maybe we're wait, what's the story with granite? Why are we talking about that? This rock, your common rhyolite, and your granite are chemically identical, same minerals. In fact, if you look at most rhyolites under magnification, you'll actually see the same crystal pattern, the same crystal colors you see in a granite. And I've got some photographs to back that up. We'll try to do a little of that in our lab if we have a lab together. So, thanks once again for joining me at this little whistle stop Obsidian Cliff, and we'll tune in for the next one on day 7.